fourth lecture on the theory of small oscillation. In the first two lectures, we have introduced the subject small oscillation, what do we mean by small oscillation, and emphasized on the stability analysis for system having 1, 2 and 3 degrees of freedom. In the last lecture, that is in the third lecture, we have started formulating the general theory of small oscillation using generalized coordinates. Before going to today's topic, let me recapitulate what we did in the last class. We introduced a generalized coordinates eta I, which represents qi minus qi0. That is, it represents the displacement from the stable equilibrium point corresponding to the ith degree of freedom. Then we write the kinetic energy T as some summation over I and j running from 1 to n degrees of freedom, Tij, then eta I dot, eta j dot, and in matrix form we wrote this relation as eta dot, T matrix, eta dot, where T is an Hermitian matrix. Similarly, V where potential energy was written as summation over Ij is equal to 1 to n Vij eta I eta j, and we wrote it in matrix notation as eta V operator eta, where we have used Dirac's Biometric notation for representing the matrix as the hat over the quantity represents that it is the matrix and this is the scalar quantity. If we perform the dimensionality analysis, this is a row matrix, so it is 1 into n matrix. This is a square matrix, Hermitian n cross n, and this is an n cross 1 column matrix. So the resultant matrix is 1 cross 1, which is a scalar. And we define, furthermore, we define the kth eta as eta 1, eta 2 up to eta n. And by eta is the corresponding row matrix. So we also obtain the Lagrangian of the system. The Lagrangian was defined as T minus B, and this is for a conservative system and oscillating above the stable equilibrium point is Ij is equal to Tij eta I dot, eta j dot minus Vij eta j, and the corresponding Euler-Lagrange equation for, if we write del LT of del L del eta dot del L del eta k dot minus del L del eta k is equal to 0. This leads to the equation that summation over I is equal to 1 to n Tik eta k dot plus Vik, sorry, Ti eta I is equal to 0. This is n coupled equation. There are, for k is equal to 1 equation, k ranges from 1 to n. So there are one equation for each value of k, so there are n equation and they are the coupled equation. Sorry, this should be doubled up. Now, this much we have obtained in our last class, and in matrix notation it reads as eta double dot plus V matrix operating on eta is equal to 0. So this much we obtained in our last class. So today we shall start from this relation and go further. So, so this is our starting expression for today's class. This is summation over I is equal to 1 to n, and for this k I am replacing by j. So this is Tij eta I double dot plus Bij eta I is equal to 0, or the matrix form. The matrix form allows us to write the expression in a very compact way. Now we are to solve this equation. Since we are solving solving for a system which oscillates with small amplitude about its stable equilibrium configuration, we assume a solution or trial solution as eta I as a function of time is equal to ai, its amplitude, e to the power I omega t, where ai in general may be a complex quantity, and we can write ai is equal to ai modulus e to the power I phi I, where is the phase, or we may write it as some in terms of two real quantities, say alpha plus I beta. If we write this in matrix form, the matrix form of this relation is eta t ket is equal to a e to the power I omega t. What we have assumed in this solution, in this trial solution, we have assumed that the system is, for each degree of freedom, is executing a true of 2 and 4 oscillatory motion about its stable equilibrium configuration. If we plug this equation into this, what we get? Firstly, if we differentiate it twice with respect to time, this is minus omega square ai e to the power I omega t. If we write the corresponding matrix form, eta t double dot is equal to minus omega square a to the power I omega t. So if we put this equation here, we get I is equal to 1 to n. From I am writing this term first, so this is Vij, and ai will be common, and minus omega square Tij ai is equal to 0. We have omitted the term e to the power I omega t, which is common in everyone. In matrix form, this equation reads as V operating on A minus omega square T operating on A is 0. This is the matrix form. At each and every step, I am writing the matrix form because in the case of complicated expression, it will be found to be convenient to write the matrix form rather than its component form. So, if we want to solve this is a set of n simultaneous linear homogeneous equations in AIs. So our objective is to find out the AIs. So for non-trivial solution, let me define a trivial solution is one for which AI is a 0, all AI is a 0. For a trivial solution, AI is equal to 0 for all I. This does not remove the dynamics of the system. So although it is a mathematically acceptable solution because this solution do satisfy this set of coupled equation, we do not include it as a solution for a physical dynamical system. So for non-trivial solution, the secular determinant should be 0. The secular should be 0. That is to say that the determinant p minus omega square t, this should be 0. This is known as the secular determinant. If we write it in longhand, it gives you v11 minus omega square t11, v12 minus omega square t12, right up to v1n omega square t1n, then v21 omega square t21, v22 minus omega square t22, v2n minus omega square t2n, vn1 omega square tn1, vn2 minus omega square tn2, vnn omega square tnn. This determinant is 0. When we unfold it, this gives you an algebraic equation. This gives you, what we get is an algebraic equation of nth degree in omega square, which says that there are n values, so nth degree algebraic equation in omega square, so which gives you n roots of omega square. Let us denote it as omega square k, where k is less than n, greater than 1. So there are n values of omega square. If all the omega squares are different, we call it a degenerate case, and if more than 2 omegas have the same value, say omega 1 is equal to omega 5, then we call it a doubly degenerate case. So we have n values of omega square, and since we are dealing with a linear differential equation, so the most general solution, this is a linear differential equation, so most general solution is the linear superposition of all the solutions. So this equation now modifies to this equation now modifies to a bit complicated equation, which is now applying superposition principle. We write in component form, eta I t is equal to summation over k is equal to 1 to n a k I e to the power I omega k t. So that the solution is, say for example, eta 1 of t is equal to a11 e to the power I omega 1 t plus a1 e to the power I omega 2 t right up to a n1 e to the power I omega n t. And a's are independent of time. If we write it in matrix form, this equation now reads as summation over k is equal to 1 to n ak e to the power I omega k t. This is the matrix form. Now if we now plug this equation into this, what do we get? This equation, now the solution is no more this, we know the solution is this. So there we will have two sums, one sum is over I, another sum coming from k, and this is Tij. For this it is first let me write this term. This is Bij. For eta I we write, for eta I we now write this one. So k sum is over there, a ki, and this is there, and then we have Tij a ki omega k square. This is equal to omega square e to the power I omega k t is equal to 0. And this here the k sum runs from I and k, both the sum runs from 1 to n. Now if we write it in matrix form, we can write it as, this form is written as Vak minus omega k square T ak is equal to 0. This is the matrix form corresponding to this relation. Firstly, before proceeding further, we like to focus our attention on the nature of omega square, or we would like to justify that the system, if we study the system about the stable equilibrium position, then it indeed represents as oscillation. So we rewrite this equation as Vak is equal to lambda k T ak, where lambda k is equal to omega k square. This is the equation for kth eigenvalue, and we write another equation for the nth eigenvalue. This is the equation for kth mode, and this is for lth mode. If we take the Hermitian conjugate of this equation, this is the Hermitian conjugate of this, then this left hand side it is bra L times V dagger. Since V is a Hermitian, V dagger is V on this side we have lambda L star AL T. Again, T dagger is equal to T because T is Hermitian. We multiply this equation from the left. So we multiply this equation from the left by bra AL. So this equation is AL V AK. We multiply it from the left by bra AL, and on the right hand side we have lambda K AL T AK. And if we multiply this equation from the right by AK, we get AL V AK is equal to, sorry, this okay, and this is lambda L star AL T AK. If we subtract one equation from the other, we get that if we call this is equation 1 and this is equation 2, then 1 minus 2 gives, these two terms are same, so they cancels out. So we get lambda K minus lambda L star. Then we have AL T AK is equal to 0. This is an important relation. So we get, now we get this relation. If we consider the non-degenerate case, then for non-degenerate case, for L not equal to K, the lambda L and lambda K are different, and obviously in that case this part should be 0. And it is a scalar quantity, as you know, that this is 1 into n matrix, this is n into n, this is n into 1, so it is 1 into 1, it is a scalar quantity. So what we get? So in general we get the lambda K minus lambda L star AL T AK is equal to 0 for L not equal to K and for degenerate case. Obviously, we have lambda L not equal to lambda K, which gives you AL T AK is equal to 0. This is an important relation which is often sometimes referred to as the orthogonality relation. Now we see one point. The secular determinant, from secular determinant we get n different values of omega square. If we say put omega square is equal to omega 1 square in the determinant and go for solving the AI case, then it will be found that we can find n minus 1 values of A in terms of other. This feature we have also noticed while diagonalizing a matrix. So there we found that for if we have a matrix of order n, square matrix of order n, then when we want to find out its eigenvectors, then the n minus 1 components of the eigenvector could be expressed in terms of 1, and the remaining coefficient or component was found by normalization. Here we put a different type of normalization condition. Let me see what happens. So we know this is 0 for L not equal to K. Our aim is what happens if we calculate this one. Same, K L is equal to K, that is what happens to the this matrix element when L is equal to K. let us consider that A of K, which is a complex quantity which we denoted earlier, we write it. So we assume that AK is a complex. Recall that we have written that AI is a complex, so we wrote it as AI e to the power I phi I. So this is another way of writing this. So if we write then this quantity, if we call it Z is equal to AK T, okay, this becomes, if we take the corresponding bar equation, it is alpha K plus, minus I bar beta K, then T operator, and for AK we write alpha K plus I beta K. So first is this multiplied by this, so the result is alpha K T alpha K, and then this multiplied by this sandwiched with T. So T is sandwiched between these two. So this is beta K T beta K. Then I have I. T is sandwiched once between these two. So this is with plus sign alpha K T beta K, and this is with minus sign beta K T alpha K. Now recall one thing, that the property of Hermitian matrix. For a Hermitian matrix, we know that H operating on A gives you some mu times B, right? B is another vector. It may not be an eigenvalue equation. Then if we take the Hermitian conjugate of this, we get the Hermitian conjugate of this equation is A, H dagger, which is equal to H, is equal to mu bar B. Now, if we multiply this, the first equation, from the left by bar B, then this becomes mu times bar B. And if we write this equation from the right by bar B, we have, and if we subtract between these two, so these two, when we subtract these two, we get that A H B is equal to B H A. This is another definition of Hermitian matrix. The Hermitian matrix could be defined in two ways. One is H dagger is equal to H. This is one definition. Or in terms of matrix element, it is the definition of Hermitian matrix. Since T is Hermitian, this is 0, as T is Hermitian. This is the adjoint form of definition of Hermitian matrix. So we see that the quantity Z, which is the T sandwiched between AKs, is equal to this. So if we consider a particle moving with velocity alpha k, then it is the kinetic energy of a particle moving with velocity alpha k, and this is the kinetic energy of a particle moving with velocity beta k. So these are of the form twice t, so it is necessarily greater than 0. So we see that if L is equal to k, so what we get? For L is equal to k, we see that lambda k minus lambda k star. This is for L is equal to k. We have ak is equal to 0. Since this is not 0, as we have proved, so which shows that lambda k star is equal to lambda k. So which says that omega k square is real. It doesn't yet prove that omega is real. Omega k square is real. So what we get if we look back into the equation? The first thing, this was 0, and now we redefine it that ak Pak is equal to 1. We may define, because this quantity is a finite quantity, and we can set it as 1, so that these two equations combinedly reads as ALT AK is equal to delta LK. This is a very important relation, and this replaces the normalization condition that we are used to use in the case of matrix eigenvalue problem. So this is known as the normalization condition. How does it look like in component form? Because the book that you generally uses this relation in its component form, and sometimes the component form, as I have remarked earlier, is not easier, rather than the compact notation is easier. Now if we write this relation in component form, it is AL T operator AK is equal to delta LK. If we take the component form, we write it that summation over ij. First, this is we have the AL, this Lith element. Lith element, since it is the transpose, so it is IL, the ordering is interchanged, then Tij, and this is Aik is equal to delta Lk. This is the relation that you are habituated of looking at the text. So this is the normalization condition. It is in matrix form, and this is in component form. Now going back to the mother equation that we started with, we have V matrix operating on AK is equal to lambda K, T matrix operating on AK. So if we multiply this equation from either side by AK, we get AK, VAK is equal to lambda K or lambda K is equal to omega K square is equal to So now we have seen that this is comparable to twice T. This is comparable to twice the kinetic energy, and it is essentially positive. So this denominator is a positive quantity. What happens to the numerator? Consider the Ij, the matrix elements of V matrix, Vij. These are basically twice V del Qi del Qj obtained from Q vector Q is equal to Qj the equilibrium position. Since it is a stable equilibrium condition, so this is greater than 0. So the numerator is also greater than 0. So this is a positive quantity, which says that omega k is real. Let me summarize what we have. First, we prove that omega k square is real. Then we have obtained a relation which gives us the value of omega k square, and we have shown that omega k square is positive, that is omega k is real, which indeed ensures that the oscillation persists. Because if we have omega k is complex, say omega k can be written as k plus I rho, then the solution e to the power I omega k t would be e to the power I k t times e to the power minus rho t. This would show an exponential damping. So then the oscillation will not persist, it will die down with time. But we are considering the persistent oscillation, small amplitude oscillation. So one of the requirements for such oscillation is that the eigen-frequencies omega k should be real. This analysis ensures that the omega k's are indeed real. So we shall continue our discussion in the next class. So let me summarize what we have done in this class. We have first used solved the eigenvalue problem. So we got the secular determinant which gives the values of eigen-frequencies. Then we have written the equation of motion and imposed the normalization condition, that is the normalization condition in terms of the T matrix. Then we found the expression for the omega k square and has assured that omega k are indeed real, so that we get a persistent oscillation, small amplitude oscillation above the stable equilibrium point. If we could study the oscillation about an unstable equilibrium point, in that case Vij would be unstable, Vij would be negative, and which leads to omega square is negative. In that case omega will be a complex quantity, and that leads a damped oscillation. So this is the reason that we study the small amplitude oscillation only about stable equilibrium position. That's all for today.